Hi, everyone. Thanks for joining us today. My name is Adrienne Stenz, and I'm the Application Development Engineer here at YSI. And today I'm joined by Dr. John Welsh, who is a Senior Product Manager. Whether you work in drinking water or wastewater, chlorine is likely a part of your disinfection strategy. Today's webinar will explore the difference between online DPD analyzers and amperometric chlorine sensors, helping you choose the right measurement method for your chlorine disinfection process. Here's an overview of what we will cover today. We will start with chlorine chemistry and disinfection basics before discussing the different types of chlorine you can measure, free versus total. Finally, we will discuss the online chlorine measurement methods available for municipal water, DPD analyzers, and amperometric sensors. Let's begin by talking about why chlorine disinfection matters. Chlorine is a powerful disinfectant that kills or inactivates 98 to 99% of harmful pathogens in water, including bacteria and viruses, which are harmful to human and animal health. Water chlorination has been used for over 100 years to protect the public from many serious waterborne diseases, including typhoid, cholera, and dysentery, which used to be major health problems before chlorination was first instituted in the United States in 1908. Chlorine is tightly regulated in both drinking water and wastewater industries, as enough chlorine is needed for proper disinfection, but too much chlorine can cause harm to the public and to the environment. So what is chlorine exactly? Well, chlorine is a chemical element. It's found here on the periodic table in between fluorine and bromine. Chlorine is a powerful oxidant, which means it has a high tendency to steal electrons from other compounds, which makes it a very powerful disinfectant. In its elemental form, chlorine is found in the diatomic form, Cl2, which is a gas at room temperature and pressure and very reactive. Elemental chlorine can be liquefied by compressing that gas under pressure and cooling it. The liquefied form is what's stored and transported in cylinders and is a highly concentrated form of 100% elemental chlorine. Chlorine is used in many industries for disinfection. One very common use is within public water supplies, such as drinking water disinfection and wastewater disinfection, where chlorine is the most common disinfectant used to kill germs. It's also commonly used to disinfect swimming pools, to destroy any harmful bacteria or algae, and break down organic matter like sweats and oils to ensure water is safe. Chlorine is also used in household cleaners. Bleach is made of sodium hypochlorite, which is used to disinfect surfaces at home. Chlorine is the most common disinfectant used in public water systems for several reasons. First off, it's easy to obtain. The process for manufacturing chlorine only requires salt, which is sodium chloride, NaCl, as an ingredient. The manufacturing process is called the chlor-alkali process, which involves taking a concentrated salt brine and applying electricity to separate the sodium and chloride molecules, leaving chlorine gas as a product. It's also very economical. The other byproducts of that chlor-alkali process are hydrogen gas, which is often used as an energy source, and sodium hydroxide, which is a popular chemical used in manufacturing, especially in the use as a pH adjustment. It's also extremely effective. Chlorine kills a broad spectrum of bacteria in water and also provides a lasting residual or protective effect important for drinking water systems, preventing regrowth of microorganisms in pipes in the water distribution network. And lastly, chlorine disinfection is generally an easy process to implement. Chlorine processes do not require a large footprint, and the mechanical parts are generally minimal for maintenance. Chlorine can be dosed in several forms into municipal water, including in its elemental form of liquid chlorine, also known as chlorine gas, which is available as a compressed gas at 100% strength. The most common ways of adding elemental chlorine to a stream are to feed gas with a vacuum-operated solution feed system or to feed the gas under pressure. Chlorine can also be dosed in a liquid form of sodium hypochlorite, also commonly called liquid bleach, which is commercially available in strengths of approximately 15% by weight. This can be added by chemical metering pump or by physically dumping it. Chlorine can also be dosed in a solid form of calcium hypochlorite, referred to as powder chlorine, which contains 70% available chlorine. It can be added by use of pellets or by mixing a solution of water and calcium hypochlorite and using a small chemical feed pump. And then finally, chlorine can be dosed in the form of chlorine dioxide, which is a gas which is unstable and decomposes rapidly in air and water. Chlorine dioxide has a more potent disinfecting ability than elemental chlorine because it has more active oxygen atoms available to react and oxidize substances. It's generally 2.5 times more potent than elemental chlorine on a multimole basis. Chlorine dioxide is produced with an on-site generator and then injected into the water. No matter the form of chlorine used, the effect of chlorine when it reacts in water is the same. When whatever form of chlorine reacts with water, H2O, it forms two compounds, hypochlorous acid, which is HOCl, and hypochlorite, OCl. Hypochlorous acid will partially dissociate into hydrogen ions and hypochlorite ions. The equilibrium between these two forms, hypochlorous acid and hypochlorite, depends on the water's pH. At lower pHs, the reaction tends more towards the left, towards hypochlorous acid, and at higher pHs, the reaction tends more towards the right, towards hypochlorite. This is important because hypochlorous acid is the most potent disinfectant. It is about 80 times more powerful than hypochlorite and is the primary agent responsible for disinfecting microorganisms during water treatment. Thus, the production of hypochlorous acid is always targeted for disinfection by maintaining a certain pH in the water. So what exactly is that pH that's used for chlorine disinfection? Here's a look at a graph that shows pH and the percent of each form of chlorine that exists. The ideal pH for chlorine disinfection is generally considered to be between 5.5 and 7. 5.5 pH maximizes the production of hypochlorous acid, but can also lead to corrosive water, which can damage water distribution pipes. Any pH higher than 7, you risk losing disinfection potential to hypochlorite, and any pH lower than 5.5, you risk losing chlorine as elemental chlorine, which is poisonous to most living organisms. So how exactly does chlorine disinfect water? Chlorine kills or inactivates pathogens in water through oxidation or through the transfer of electrons. This oxidation process disrupts the cell membrane of pathogens, rendering them incapable. In general, hypochlorous acid and hypochlorite ions oxidize or steal electrons from the cell wall of bacteria, causing physiological changes to those pathogens. Hypochlorous acid also attacks and penetrates the cell wall of these pathogens and enters their cytoplasm, which causes the release of vital cellular components, effectively killing the bacteria. Chlorine disinfection kills or inactivates 98 to 99% of harmful pathogens in water in this fashion, including those that cause serious disease such as typhoid, cholera, and dysentery.
All right. Thank you all for coming. Thank you, Adrian, for passing it on to me. Thank you, Shannon, for moderating. Sorry for a little miscue there. So that now that we know the basics of chlorine and its use as a disinfectant, let's talk about the different forms of chlorine that are important to distinguish in municipal water. There we go. Free chlorine refers to the portion of chlorine in water that is present as an active disinfectant, not yet combined with ammonia or organic nitrogen compounds. It is the most effective form of chlorine for disinfection and oxidation. As we saw in the previous slides, chlorine in any form, when introduced into water, forms hypochlorous acid, which exists in equilibrium with hypochlorite ion. Hypochlorous acid is a strong disinfectant and is the dominant species at lower pH. Hypochlorite ion is a weaker disinfectant and is dominant compound at higher pHs. Free chlorine is typically measured in drinking water applications. The diagram on the right shows a typical drinking water treatment process. Drinking water is always disinfected at the end of the process with enough free chlorine so that it maintains a residual for the distribution network, protecting it against any pathogens that might exist in the network before it reaches the customer's taps. However, in some cases, chlorine could be added to the top of the filter for taste and odor control. In that case, you would want to monitor chlorine at this point as well. Free chlorine is used in drinking water disinfection because it is the most effective and fast-acting form of chlorine for disinfection. However, there are some downsides to the use of free chlorine, and that is the formation of disinfection byproducts, or DBPs. The natural organic matter that might be found in source water, particularly the humic and fulvic acids, react with free chlorine to form trihalomethanes. Additionally, if the source water contains bromide, it will be oxidized by hypochlorous acid to hypobromous acid in the presence of chlorine and form bromine-containing disinfection byproducts. The 4 trihalomethanes that are of most concern to US EPA are chloroform, as shown on the right in the graphic, bromodichloromethane, dibromochloromethane, and bromoform. A second set of regulated compounds are the haloacetic acids. US EPA has set maximum contaminant levels for 5 of these compounds: monochloroacetic acid, dichloroacetic acid, trichloroacetic acid, monobromoacetic acid, and dibromoacetic acid. The THMs and HAAs are compounds that are harmful to human health. Long-term exposure to these compounds is associated with increased risk of certain cancers, including liver and gallbladder cancer. Source water and the quality of the finished water from a water treatment plant impact the tendency of these harmful compounds to form. Drinking water treatment plants are regulated by the EPA on the amount of free chlorine they can discharge. Drinking water plants are responsible for discharging enough free chlorine to protect the water in the distribution network until it reaches customer taps. In general, free chlorine residuals at plant effluents range from 0.2 milligrams per liter to to 4 milligrams per liter maximum. Anything above 5 milligrams per liter free chlorine can pose risks to human health. Disinfection byproducts, the trihalomethanes and the haloacetic acids, are also tightly regulated to ensure public safety. THMs are regulated at 80 micrograms per liter and HAAs at 60 micrograms per liter. Another form of chlorine, referred to as combined chlorine, is the chloramines. Chloramines form when hypochlorous acid reacts with ammonia and, to some extent, organic nitrogen compounds in water. These compounds are monochloramine, dichloramine, and trichloramine, or nitrogen trichloride. All chloramines have disinfectant capability, but not all chloramines are used as a disinfectant. Chloramines have a much lower standard reduction potential as compared to free chlorine. Hence, they have less ability to damage microbial cell walls, enzymes, and nucleic acids as quickly as chlorine. Monochloramine formation is chosen because it is a stable disinfectant. Dichloramine has some disinfectant ability, but it is unstable and irritating to the eyes and nose. Trichloramine is not used as a disinfectant. It is volatile, unstable, and irritating to the lungs and eyes. Dichloramine and trichloramine are those compounds that you smell when a swimming pool is not properly chlorinated. Factors that influence which form of chloramine are formed are pH and the chlorine to ammonia ratio. To target monochloramine, an ideal weight ratio of 5:1 chlorine to ammonia is targeted based on the ratio of the molecular weight of chlorine to ammonia. 1 mole of chlorine reacts with 1 mole of ammonia to form 1 mole of monochloramine. pH also impacts chloramine formation. Monochloramine forms in the range of pH 7 to 9, dichloramine forms between 4 and 7, and trichloramines form at pH value of 4 or lower. Monochloramine is less reactive than chlorine, hence it is more stable as a disinfectant. It is also a weaker disinfectant for the same reasons. Since it is more stable, it has a longer lasting residual than free chlorine. However, it produces less disinfection byproducts, and that is the goal in a chloramination disinfection scheme. So when and why are chloramines used for disinfection over free chlorine? The first part of that answer is when operators choose to use monochloramine as the secondary disinfectant in a distribution system. The why part of that answer is to reduce the formation of DBPs in the distribution system. There is one important aspect to our chloramination scheme for disinfection that cannot be overlooked. Monochloramine is a weaker disinfectant than free chlorine. Therefore, a typical disinfection scheme will involve the use of free chlorine as the primary disinfectant and the addition of monochloramine as the secondary disinfectant in the distribution system. Of course, the measured parameter will also change in a chloramination system. Since we are now concerned with the measurement of combined chlorine, the total chlorine determination is critical. Total chlorine gives a full picture of the amount of chlorine in a water sample. It is defined as the sum of free chlorine plus combined chlorine. Online instruments are more capable to measure free and total chlorine in near real time. To determine the concentration of chloramines in a sample, you would take the total chlorine measurement minus the free chlorine measurement, or use an analyzer that is specifically designed to directly measure monochloramine. In wastewater, the primary goal in a wastewater treatment application is to disinfect water before it is discharged into a body of water or reused for drinking water. Proper disinfection ensures that the water meets regulatory permit limits for indicator organisms such as E. coli, fecal coliforms, or enterococci. There are secondary goals as well, like the reduction of nuisance organisms, algae, slime, and odor-causing compounds. These goals must be balanced with the discharge of residual chlorine that can harm aquatic life. Therefore, wastewater plants often use dechlorination after disinfection to remove excess chlorine. In both cases, disinfection and dechlorination, total chlorine is measured to provide a complete assessment of the amount of chlorine in the water. The MPDES regulates the amount of total chlorine that can be discharged from wastewater facilities. Typical limits vary from 0.01 to 0.1 milligrams per liter, depending on the state and the permit. Utilities are responsible for dechlorinating wastewater before it is discharged in order to protect the environment. So now let's move on to part 3, the chlorine measurement technologies, DPD versus amperometric. I will start with the DPD part of the presentation. Here we go. All DPD analyzers are based on the principle of colorimetric analysis for the determination of chlorine concentration using N,N-diethyl paraphenylene diamine, or DPD, as the reagent. I will be talking today specifically about the YSI Model 3017M. The Model 3017M is a bit unique in that the water stream continuously flows through the flow cell. At a predetermined time, the buffer and indicator reagents are added to the flowing sample. This is referred to as flow injection analysis. The reagents and water are thoroughly mixed in the mixing section of the flow cell. If chlorine is present, the water sample turns color from clear to purple. The intensity of the color change is proportional to the concentration of chlorine. The absorption of light is also proportional to the color change and is translated into chlorine concentration through the calibration of the analyzer. The choice of measuring either free or total chlorine is made by the selection of the reagent. For free chlorine, DPD reacts with chlorine. For total chlorine, potassium iodide is added to the buffer. Potassium iodide is oxidized to iodine by the chloramines, and it is iodine that reacts with DPD to produce the color change. The 3017M is a fairly simple analyzer with only 6 main components. It has an onboard display that is backlit and visible through the door. With its onboard display and keypad, plus built-in communication protocols, you can operate the 3017M without a controller. This is an onboard display that can communicate with SCADA via 4 to 20 milliamp or Modbus. There is a peristaltic sample pump that continuously flows sample through the flow cell. The reagent pump is also a peristaltic pump that injects the buffer and indicator at predetermined times. The measuring cell is where the DPD reaction occurs and chlorine concentration determined by absorbance of light from a 525 nanometer light source. This is the terminal block where power and communication connections are made. And then lastly, a compartment where the indicator and buffer reagents are housed. The 3017M is a DPD colorimetric analyzer for the continuous measurement of free or total chlorine in drinking water and wastewater samples. The online analyzer can be used in municipal water applications to help monitor and control the chlorination or dechlorination process. The 3017M is low maintenance, uses EPA-approved DPD methodology, and is suitable for drinking water and wastewater reporting in the United States. The 3017M was designed with the operator in mind. To that end, it is fully field serviceable. The chart below provides the recommended schedule for the most critical service tasks. Even the flow cell, which I consider the heart of the analyzer, is field serviceable. If the situation warranted, the entire flow cell could be replaced in the field. Every analytical technique has its pros and cons, and the 3017N and DPD measurement are the same as well. Some of the pros: compliant standard measurement technique for chlorine. It comes factory calibrated and does not require user calibration. It is not affected by the sample's flow rate, pH, temperature, or pressure. It also comes with a sample inlet device that can be installed directly into the process stream. And it has a predictable maintenance schedule. Some of the disadvantages: it does require reagents. It is also discontinuous in the sense that it doesn't have a constant output. The minimum cycle time is 160 seconds, and that can be extended out to 24 hours or once a day if you so choose to do that. It is affected to some extent by iron, manganese, and other oxidants if these are present in the sample. It will have a slightly higher operational and maintenance footprint because of waste handling, tubing replacement, and reagent replacement. So this concludes my section of the presentation on the types of chlorine and DPD, and I think we'll hand it back over to Adrian.
Awesome. Thanks, John. Share my screen. All right, now let's talk about another chlorine measurement technique, which is amperometric chlorine sensors. Amperometric chlorine sensors work by determining the chlorine concentration via two dissimilar electrodes. These sensors have a specific membrane for chlorine, which diffuses through. Once chlorine diffuses through that selected membrane, it reacts with a working electrode, or cathode, which is typically made of gold. At this working electrode, the chlorine species is reduced to chloride, or Cl-, gaining electrons in the process. That chloride that is produced at the working electrode then reacts with a second counter electrode, known as the anode, typically made of silver. When chloride reacts with the silver electrode, it forms the compound silver chloride, and as it forms this compound, it releases electrons. These reduction and oxidation reactions happening at the working electrode and at the counter electrode create a flow of electrons within the sensor, resulting in a measurable electric current. That produced electric current is directly proportional to the concentration of chlorine in the water sample. YSI offers IDS amperometric sensors for monitoring free or total chlorine. Some of the features of the YSI amperometric sensors are that they utilize a potentiostatic 3-electrode system. So our YSI sensors contain not 2, but 3 electrodes within them, a gold working electrode where the chlorine species is reduced to chloride, a stainless steel counter electrode where chloride is oxidized, and a third silver-silver chloride reference electrode, which outputs a constant reference potential at all times. In traditional two-electrode amperometric sensors, the counter electrode also acts as a reference electrode, but this gives it the potential to drift over time. This three-electrode design separates the functions of the counter electrode and the reference electrode, which results in a more stable reference potential and less drift, as well as higher accuracy and sensitivity at low chlorine levels. These sensors are also largely pH independent. The free chlorine version of this sensor accepts chlorine in the form of dissolved Cl2 gas, hydrochloric acid, hypochlorite, and chlorine bound to cyanuric acid, which is important for swimming pools. Traditional amperometric free chlorine sensors only accept hydrochloric acid, and as we know, other forms of free chlorine, such as hypochlorite, may be present in solution based on pH. So these traditional sensors require a separate pH sensor to adjust their readings and account for the solution's pH. Since the YSI free chlorine sensor accepts all forms of free chlorine, it is largely pH independent in the pH ranges of 4 to 9, requiring no separate pH adjustment. There are free and total chlorine versions available of this sensor. The total chlorine version has a specialized electrolyte formulation that converts combined chlorine into a measurable species once inside the membrane. And lastly, these are temperature compensated with an integral temperature sensor. Here are the parts of the YSI amperometric free and total chlorine sensor. First is the membrane cap, which holds the membrane in place at the very bottom of this cap. This membrane is a selective barrier for either free or total chlorine species to diffuse through. Inside this membrane cap is a temperature thermistor to automatically account for temperature. Electrolyte solution fills the membrane cap. This solution is typically made of potassium chloride, which acts as a conductive medium for the redox reactions occurring at the electrodes. For the total chlorine version of this sensor, the electrolyte solution is made up of potassium iodide to convert total chlorine into a measurable form. The electrolyte solution and the membrane must never be allowed to dry out. These two components are critical for the sensor's function, and allowing them to dry out will cause the sensor to fail. The membrane cap covers the following internal electrodes. The working electrode, which is made of gold, is where chlorine species are reduced to chloride. Gold is used because it is inert and highly conductive. The reference electrode is located just above the working electrode and is silver chloride. It produces a stable, reproducible reference potential against which the working electrode's potential is measured and controlled. In this three-electrode setup, it's designed to pass no current through the reference electrode, which keeps its potential stable. And then finally, the counter electrode is located up here, which works to complete the electrical circuit with the working electrode. Current is passed through the counter electrode to balance the current produced at the working electrode. So reduction occurs at the working electrode and an oxidation occurs at the counter electrode. The magnitude of the current is measured, which is converted into a chlorine concentration based on a calibration curve. Our amperometric chlorine sensors come in a pre-configured panel called the water monitoring panel. Amperometric sensors are sensitive to sample flow rate, pressure, and other conditions. So placing them in these pre-configured flow cells ensures consistent sample conditions at all times for these sensors. These panels can measure or can include up to 4 flow cells with options to measure free chlorine, total chlorine, electrochemical DO, ORP, pH, and conductivity. The panel is configured to work with an IQ SensorNet controller, which has versatile communication options. You can communicate with SCADA via analog or digital signals. You can also directly control relay actions using specific modules of IQ SensorNet, or add additional IQ SensorNet sensors onto this system. The panel also features a built-in maintenance station for easier calibrations and maintenance of these sensors, and is a low-flow design. The amperometric chlorine sensors require a minimum flow rate of 15 liters per hour for measurement. When it comes to maintenance of amperometric sensors, the following things are required. Calibration is required to keep these sensors accurate for your water. We recommend calibrating this sensor monthly against a DPD reference test. That way, you know the sensor signal matches a trusted standard. Every 6 months, the sensor's electrolyte solution must be refilled, which is shown on this picture on the left. This keeps the internal chemistry stable and cannot be allowed to dry out. Every 12 months, the membrane cap should be replaced. Over time, these membranes can foul, stretch, or lose performance. Whenever you refill electrolyte solution or replace a membrane cap, the sensor must be repolarized. Polarization involves placing the sensor in a well-stirred solution of at least 5 milligrams per liter chlorine for an hour to establish a potential between the working and the reference electrode. The sensor should then be allowed to sit in its flow cell in sample conditions for at least 20 minutes before it's calibrated. And finally, routine cleaning is also important. Rinsing the gold electrode and membrane cap with clean water to remove any deposits. And if the gold electrode shows discoloration or buildup, polishing it carefully with a polishing strip. If you stick to these steps, electrolyte solution every 6 months, membrane every year, cleaning as needed, and monthly calibration, you should get stable, accurate chlorine data and long sensor life. In terms of the pros and cons of amperometric sensors, in terms of strengths, they are reagent-free, so there are no reagents to replenish monthly and no ongoing costs associated with that. They also don't produce a chemical waste stream from those reagents that you have to dispose of, like DPD analyzers do. They are continuous, unlike DPD analyzers, which take a measurement every couple of minutes. Amperometric sensors are always reporting live data, which makes them useful for picking up instant changes in water quality. Another benefit is high sensitivity at low chlorine levels. These sensors can measure into very low ranges, offering a higher sensitivity compared to DPD analyzers. And finally, they're unaffected by the interferences that affect DPD analyzers, including color or turbidity, so they can give a clean signal in places where the colorimetric method might have interferences. Now, in terms of cons, they do require regular calibration against a reference method like DPD. So though you don't have to replace reagents monthly, you do have to calibrate them monthly. They are not a compliant standard method for chlorine like DPD, so you can't use them for compliance reporting. They are sensitive to water chemistry changes, including flow, pressure, pH, temperature, and chlorine variations greater than 20%. They need a stable sample environment, which is why they're installed in a flow cell on a panel to control some of those variables. And finally, they do require periodic maintenance. The membrane and electrolyte must be replaced on a schedule. The sensor must be repolarized occasionally, and the gold electrode requires periodic cleaning and polishing. Here's a side-by-side comparison of the two technologies, the 3017M DPD colorimetric analyzer and the free and total amperometric sensors. They do have different measuring ranges available. The 3017M DPD analyzer can detect 0 to 5 milligrams per liter free or total chlorine with an accuracy of 0.03 milligrams per liter. The reagents determine whether free or total chlorine is measured. For amperometric sensors, there are 3 versions available. 0 to 2 milligram per liter free chlorine, which has an accuracy of 0.005 milligrams per liter, or 0 to 20 milligrams per liter free chlorine, which has an accuracy of 0.01. So a larger measuring range is available for free chlorine and at a higher sensitivity with amperometric sensors. For total chlorine, these amperometric sensors are available from 0 to 2 milligrams per liter with an accuracy of 0.01. So a smaller measuring range for total chlorine when compared to DPD analyzers. In terms of interferences, iron, manganese, and other oxidants that might react with DPD will affect the DPD colorimetric method. Amperometric sensors are not affected by those interferences, but they are dependent on consistent pH, temperature, flow, and pressure. Additionally, the chlorine concentration of the sample cannot fluctuate by more than 20% from what the sensor is calibrated to, as the sensor cannot pick up on variations that large. In terms of maintenance, the 3017M's reagents have to be replaced monthly, whereas amperometric sensors have to be calibrated monthly. Every 6 months, the peristaltic pump tubing on the DPD analyzer has to be replaced, versus every 6 months on an amperometric sensor, you have to refill the electrolyte solution and repolarize it. Additionally, every year, the amperometric membrane cap has to be replaced. In terms of cleaning, the optics or flow cell of the DPD analyzer has to be flushed out as needed with bleach solution. And for amperometric sensors, the electrode has to be cleaned with clean water and polished with a polishing pad as necessary. When it comes to applications for YSI DPD analyzers and amperometric sensors, for controlling drinking water and wastewater disinfection processes, we typically recommend the DPD analyzer. DPD is a trusted, reliable measurement of free or total chlorine, which is necessary for controlling these types of processes. DPD analyzers have a high accuracy across the range typically used in these processes. These analyzers can be installed outdoors and have an accessory, the sample inlet device, which can be installed directly in the process stream to ensure the analyzer always has access to fresh sample. Additionally, DPD analyzers can be used at drinking water or wastewater effluent for compliance reporting, as they are EPA and ISO compliant. When it comes to monitoring in the distribution network, an amperometric sensor panel installed might be a better fit. These can be installed in a cabinet or indoors in a secondary dosing station within the network, if applicable. You could monitor free chlorine, total chlorine, or both on the same panel if chloramines are being used for the secondary disinfectant here. They don't require monthly reagent replacement like DPD analyzers, which may be difficult to keep up with in these locations when there's not regular maintenance staff. Additionally, these panels can provide continuous data, including on other parameters such as conductivity or pH, which also might be of interest for measuring there. They do require line power for the IQ SensorNet system, but that system can be set up to send automatic alerts to maintenance staff if levels ever fall out of an expected range. For other industrial process monitoring, they may be better suited by an amperometric sensor as well. These come on a pre-configured compact panel with other parameters that may be of interest, and they exhibit high sensitivity at low chlorine levels for monitoring high-quality industrial water like that of cooling towers. In summary, both DPD analyzers and amperometric sensors serve an important purpose. For process control and reliable compliance, DPD is the gold standard. It's proven, trusted, and gives operators the confidence they need for compliance and day-to-day decision-making. Automating disinfection processes with DPD analyzers can ensure reliable compliance and lead to lower chemical costs as opposed to relying on grab samples or timers to control disinfection processes. On the other hand, amperometric sensors may fit in applications where DPD analyzers do not. They are reagent-free and not affected by the interferences that affect DPD analyzers. They are a good fit for low-range, high-sensitivity chlorine monitoring, especially when you want to monitor other parameters such as pH, ORP, electrochemical DO, and conductivity in a panel environment. Both require maintenance, but in different forms. DPD requires regular reagent replacement, while amperometric sensors require regular calibrations. Together, they help utilities deliver safe, reliable water efficiently and with confidence.
Well, thanks, Adrian and John, for that very informative presentation. We'll now move on to the Q&A portion. We have just a few minutes here to answer some questions. I know our other panelists have been hard at work answering questions live. So if we don't get to your question, we will follow up with you after the webinar. And if you think of something else, as Adrian mentioned, please feel free to reach out to us. We'll start with, do chloride ions naturally presented in wastewater interfere with the amperometric method for free and total chlorine analysis, and how to compensate? We have John on the line.
Okay, my video's back on, I think.
Yeah, we can see you, John.
Thanks. No, naturally occurring chloride ions should not affect an amperometric method, either free or total. Because I do not think they would dissociate to the extent where they would, affect the measurement.
Okay. Next question. Can the 3017M be used in outdoor applications?
Yes, it can. If it's properly housed, depending on, at least covered on three sides to protect it from the elements. We have numerous of them in outdoor applications. And if it were a more hostile type of environment, for lack of a better word, then we might want to house it in a secondary enclosure, which we've done as well.
Thanks, John. Next question. Is there a benchtop meter for the YSI sensor for use in a laboratory?
Good question. I'm not sure. I know that we do have a handheld offering we use for reference measurements, sometimes with the 3017M. I'm not exactly sure which laboratory product makes or can perform the chlorine measurement. I'd have to find that out for you.
I know the multi-lab uses the IDS amperometric sensors.
Yeah, I would think it would. Yeah.
So the multi-lab is the benchtop version for your total amperometric chlorine. And then we do have a DPD handheld. I would have to
Yeah.
check on the name.
Yeah, I can't remember the name of it either.
Okay. Well, Ray will follow up with you after the webinar for the rest of the answer to that question. Next question. Can the YSI amperometric sensor, I'm sorry, that's not the right question. Let's revisit this. I think Adrian touched on this on slide 39, but what type of application determines which analyzer sensor is preferred or more suitable than the other?
Yeah, it depends kind of on your application. If you have a specific application that you want to reach out about and give us some more background information, we'd be happy to help you. In general, for controlling chlorination or dechlorination processes, the DPD analyzer is the reliable, accurate, trusted chlorine measurement that we would recommend for those types of processes. For more compact use cases like swimming pool monitoring, industrial monitoring, distribution network monitoring is where we typically recommend the amperometric sensor.
Okay, we have time for just one or two more questions here. The next question, sorry, I'm trying to find it, is, okay, so Jacob says he's seen literature that the DPD method can falsely measure chloramines above 0.5 milligrams per liter as free chlorine. How do you ensure that chloramines are not interfering with the free chlorine DPD method?
Well, if there, I'm not familiar with the reference. I'd like to see that one myself. But if there's nothing in the reagent to react with the chloramines, then they're not going to be detected. I'm not aware of, that reference above 0.5 milligrams per liter. Yeah, if you have the opportunity, share that with me. I'd like to see it as well too. But my thinking is that if there's nothing in the reagent to react with it, then there's not going to be an interference.